Hi, I'm Herb Gross, and welcome to lecture number 25 in our series Gateways to Algebra, where today we'll start a little mini-series on a topic called polynomials. And the way polynomials come about, and it's a real change from what we've been doing in terms of solving equations, illustrates the fact that sometimes when you make one little change in what you're allowed to do, one new command, say, can often change the subject dramatically. In other words, we're going to introduce a new command that we haven't used in our programming so far, and it's going to change the whole nature of what's been happening up until now. And so let me just show you what that command is going to be. It's a rather simple thing, and all it's going to be is called the multiply by the input command. You see, up until now, what have we done? We've said things like input x, then we might have said what? Add 3, then we might have said multiply by 2. Then we might have said add 4. Now what I'm going to do is I'm going to put in this new command, and it's going to be called multiply by the input, multiply by x. Now watch what happens. Suppose I start with 2 over here. I add 3, I get 5. I multiply by 2, I get 10. I add 4, I get 14. Notice that so far, to do any command here, all I had to do was do something to the last step I saw. In other words, no matter what the step was here, I was going to add 3. No matter what number I saw here, I was going to multiply by 2. And no matter what number I saw here, I was going to add 4. But now watch what happens. With the command multiply by x, I have to go all the way back to here and say 14 times 2 is 28. Now you see, that's not so difficult to do. But what does happen is, suppose I want to do the output now. The output is 28. If I want to reverse my steps, notice what the problem is here. To undo multiplying by x, I want to divide by x. But if I knew what x was, I wouldn't be doing the problem. So you see, this is a problem we've found before where the variable appears someplace in here so that we have to, the undoing method gets a little bit complicated. But what complicates this thing further is that this step comes all the way back to the beginning. For example, suppose I started with 3 instead. I add 3, that gives me 6. I multiply by 2, that gives me 12. I add 4, that gives me 16. Everything is going pretty much the same way. Now this says what? Multiply by x. Well, this time x is 3, not 2, so now the answer here is 48. You see, now for the first time, something that I'm doing changes dramatically as the command multiply by the input is implied. But look what happens if we try to simplify what's going on. See, we're going to input x, then we're going to add 2. Well, generically, that's written as x plus 2. Now, what do we do next? We multiply by x. See, here's the statement. I'm going to input x, add 2, multiply by x, add 3, multiply by x, add 4, and the output is going to be y. Now, I want to simplify this so the way we've done in the past, so maybe things will get easier to do when we go from the output to the input. So I say, okay, here's x. Add 2 is x plus 2. Multiply by x. Well, by the distributive property, the x multiplies the x to give me x squared, and the x multiplies the 2 to give me 2x. Well, notice something interesting that's happened already. I have 2 x terms, and I can't combine these because the 1 is modifying x squared, and the 2 is modifying x. You see, already the x's involve 2 different terms that can't be combined into one simple power of x. See, the next step says what? Add 3. So I've got x squared plus 2x. Now I add 3. Next step says what? Multiply by x. So by a distributive property, the x has to multiply every term over here. That's going to give me x cubed. Then 1 more x gives me 2x squared. And 3 times x gives me 3x. And the next step says add 4. So that's x cubed plus 2x squared plus 3x plus 4. Okay, now you see what happened over here? I cannot combine these into one term because they're all different nouns. There's an x to the third, x to the second, an x, and x means, of course, x to the 1, and no constant, no x term here means x to the 0. At any rate, this one simple command called multiply by the input forces us to give rise to a new animal that we haven't seen in this course before. The expression x cubed plus 2x squared plus 3x plus 4 is called a polynomial in x. See, a polynomial in x consists of a sum of terms. What does each term look like? Because it's a polynomial in x, each term will be x raised to a whole number power multiplied by a constant. A constant simply means a fixed number. See? And each term in the polynomial, see, poly means many, mono means one. Each term in the polynomial is called a monomial. And the adjective that multiplies the power of x is called the numerical coefficient. So in this term over here, 2x squared, okay, this would be a monomial, okay? And the 2 over here would be called the numerical coefficient, or simply the coefficient. And 2 would be called the exponent, okay? So we're now dealing with things of this particular type. So notice that each polynomial is going to be a sum of monomials. See, each polynomial is a sum of monomials. And the degree of a monomial is the value of the exponent. For example, in 3x to the fifth, 3 would be called the coefficient, and the degree of this monomial would be called 5. If you had 3x, that's the same as 3x to the 1 power. The coefficient would be 3, and the degree would be 1, because the exponent is 1. And if you have a plain old constant term, remember that a number like 4 can be represented as 4 times x to the 0, because remember that except when x is 0, x to the 0 is defined to be 1. In this case, the coefficient is 4, and the degree is 0. Now, in addition, monomials of the same degree can be combined into a single monomial. What does that mean? Remember that 3 plus 2 equals 5 is true whenever 3, 2, and 5 modify the same noun. So for example, 3x to the fourth plus 2x to the fourth is what? 5x to the fourth. 3x to the fifth plus 2x to the fifth is 5x to the fifth. You see, because the 3 and the 2 are both modifying x to the fifth, so the answer is 5x to the fifth. However, if you're given 3x to the fourth plus 2x to the fourth, you cannot say 3 plus 2 is 5 in this case, in much the same way as our old example, when you have, say, 3 dimes plus 2 nickels, you cannot write this as 5 of anything. It's not 5 dimes, and it's not 5 nickels. Of course, what we could do over here is notice that by the distributive property, 3x to the fifth plus 2x to the fourth is the same as x to the fourth multiplying 3x plus 2. In other words, x to the fourth times 3x would give me 3x to the fifth, and x to the fourth times 2 would give me 2x to the fourth. But that's not counted as being a monomial. You see what's happening over here? X to the fourth is a monomial, 3x plus 2 is a polynomial, and so what's happening over here is you're multiplying one polynomial by another, and the standard form of a polynomial is supposed to be the sum of monomials, but not a product. So in other words, even though you can factor this way, we're not really adding these to get 5 of anything. By the way, we should also review, as we're reviewing over here, that when we multiply, notice that we multiply adjectives and we also multiply the nouns. For example, when you have 200 times 3,000, the 2 times 3 gives you 6. That's multiplying the 2 adjectives. And the 100 times 1,000 gives you 100,000. Well, remember we did this when we did negative numbers, we did this when we did fractions. The whole point is that this concept follows us all the way through. In a monomial, the coefficient is the adjective, and the noun is the power of x. See, so in other words, what happens, for example, if you want to multiply 3x squared by 4x to the fifth? Well, the 3 multiplies the 4. See, we multiply the 2 adjectives, that gives us 12. Then we multiply the 2 nouns, x squared times x to the fifth. And here's another reason why exponents are important. See, if we hadn't talked about multiplying like bases before, we'd have to do it now. What's x to the second times x to the fifth? It's x to the 2 plus 5, or x to the 7th. See, 2 factors of x multiplied by 5 factors of x is 7 factors of x. So in other words, 3x squared plus 4x to the fifth is simply what? 12x to the 7th. Remember, you multiply the adjectives and you multiply the nouns, and when you multiply x squared by x to the fifth, you don't multiply the exponents, you add them. Okay? And the same thing is true about division. If you have 8x to the fifth divided by 2x to the third, what's the rule? You divide the adjectives and you divide the nouns. And if you didn't know that, I think the easiest way to handle this would be write this as a fraction, and then notice, by grouping like this, we could say that this is the same as 8 over 2 multiplied by x to the 5th over x to the 3rd, right? Because when you multiply fractions, you multiply numerators and you multiply denominators. So this is another way of writing this, which in turn is another way of writing this. 8 over 2 is 4, and x to the 5th divided by x to the 3rd by our rule for exponents is x to the 5 minus 3, and that comes out to be x squared. And again, by way of review, if you don't remember this, x to the 5th means to multiply 5 factors of x. X to the 3rd means multiply 3 factors of x, and basically all we're saying is what? The 3 factors of x downstairs cancel with 3 of the 5 factors of x upstairs, leaving us with 2 factors of x over here. Sometimes people do this thing a lot faster. They simply say what? 2 goes into 8 4 times, and 3 factors of x cancel with 5 factors of x, leaving 2 factors of x. So they'll write down that the answer is 4x squared. I don't care how you write this. By the way, it works the same way even if the bigger exponent is in the denominator. See, 2x to the 3rd divided by 8x to the 5th can be viewed as 2x to the 3rd over 8x to the 5th. The 2 over 8 reduces to 1/4. The x to the 3rd over x to the 5th can be written as what? By the rules for exponents, it's x to the 3 minus 5, which would be x to the negative 2. But if you didn't want to do it that way, you could say what? 2 over 8 is 1/4. And the 3 factors of x upstairs cancel with 3 of the 5 downstairs, leaving me with 2. So another way of writing this would have been 1 over 4x squared. However, this is not called a monomial in x, because to be a monomial in x, the exponent has to be a positive whole number. But that's not too crucial to talk about. By the way, if we're given slightly more complicated expressions, for example, suppose you were given, let's review arithmetic first. Suppose I have a over b plus c over b, where a, b, and c are numbers. What's the rule for adding fractions? The rule for adding fractions is what? If you have a common denominator, keep the common denominator and add the 2 numerators. So a over b plus c over b is a plus c over b. Now, instead of reading this from left to right, now let's read it from right to left. It says what? A plus c over b is a over b plus c over b. In other words, when you have the sum of 2 numbers over 1 number, it's the first upstairs number over the denominator plus the second upstairs number over the denominator. See, again, notice the psychology of this. Did you ever notice that? When you memorize vocabulary, let's say it's a foreign language, you tend to memorize from left to right. In other words, you tend to memorize in the direction that you're reading. So if you've learned that a over b plus c over b is a plus c over b, somehow it doesn't seem as obvious when you read that from right to left that a plus c all over b is a over b plus c over b. One of the things that we have to practice is what we call the symmetry principle of equality. We're used to recognizing the equality in the form a equals b. We have to be equally adept at understanding that that says the same thing as b equals a. We're going to say more about that as the course goes on, but it's kind of an interesting aside. Anyway, coming back to this, let's suppose that I'm given 5x to the 6th power plus 10x to the 4th power over 5x squared. You see, what I can do is write the 5x to the 6th power over 5x squared, and also the 10x to the 4th power over 5x squared. In other words, I can write this as what? 5x to the 6th over 5x squared. See, I'm thinking of this as being a, and this whole thing here is being b, and this whole thing here is being c. A over b plus c over b. The first over the denominator plus the second over the denominator. Now you see what I can do is treat each of these separately. See, in other words, the 5's here cancel. X to the 6th divided by x to the 2. 6 minus 2 is 4, so this is x to the 4th power. And 10 over 5 is 2. And 2 factors of x downstairs cancel 2 of the 4 upstairs. That leaves me with 2x squared altogether. So in other words, to simplify this, I would write it like this. By the way, something I do want to warn you about, and it's kind of important. Sometimes, instead of having the sum of two terms in the numerator and only one term in the denominator, we have the reverse of that. Sometimes we'll have what? A single term in the numerator and the sum of two terms in the denominator. Now, if this had been x squared plus 2x over 1, we could have written it how? X squared over 1 plus 2x over 1. Well, the uninitiated, the person who's just memorizing, looks at this and says, oh, this reminds me of this. I'll just write this as 1 over x squared plus 1 over 2x. But you're not allowed to do this. I mean, let me show you why. Suppose I use numbers over here. Suppose I have 1 over 2 plus 4. 2 plus 4, of course, is 6. So this answer here is going to be 1/6. Why should it be obvious to me, aside from the fact that the answers are different, that this is not the same as 1/2 plus 1/4? Let me see if you can see why. As you make a denominator bigger, doesn't the fraction get smaller? So by adding 4 to the denominator here, this fraction, 1 over 2 plus 4, is already less than 1/2. We've also added the 2 onto the 4, so it's also less than 1/4. In other words, whatever this fraction here is, it's going to be smaller than 1/2, and it's even going to be smaller than 1/4. Notice that 1/2 is already bigger than this. 1/4 is already bigger than this. So by adding both of these up, I'm going to get something that's even more large than this. Do you see the idea? In other words, keep in mind that in a fraction, when the denominator gets bigger, the whole fraction gets smaller. So actually, by adding things on over here, you're making the fraction smaller. By splitting it off this way, you're making each part bigger than the original fraction. So even though things may look like they're right, you have to check these things numerically. This happens a lot. For example, let's see if I can. For example, sometimes people will see things like 5x plus 6 over 5x. And they'll say, oh, I'll just cancel the 5x like this. Well, you can do that, but it's wrong. Now, why is that wrong? You see, this really means what? 5x over 5x plus 6 over 5x. See, here you can cancel this and call it 1. But there's still what? The 6 over 5x. The thing I want you to notice is, if you're in doubt when you're doing things like this, just put in numbers. Suppose you take 2 plus 8 over 2. Now, 2 plus 8 is what? It's 10. 10 over 2, the answer should be 5, shouldn't it? Well, suppose you just mechanically wanted to cancel. Suppose you had 2 plus 8 over 2, and you say, I just think I'll cancel the 2's. Well, do you see that that's not going to give you 5 for the answer? See, suppose you put a 1 here and a 1 here. You say, oh, 1 plus 8 is 9. The answer here is 9. No, it's not, because 2 plus 8 is 10, and 10 divided by 2 is 5. The fact that this is the right answer and this technique gives you 9 is just proof positive that you're not supposed to do this. Anyway, let's go on and talk a little bit more about our polynomials again. You see, polynomials are going to be what? They're going to be sums of monomials. And the thing that you can do is what? If the two coefficients modify the same noun, we can combine them. The other tradition that we use is we usually go from the biggest exponent to the smallest. The same way as in place value, we go from the highest denominations to the lower denominations. For example, the way I would rewrite this is I would look for the highest exponent that appeared. That's what, 2x to the 5th? That's the only x to the 5th term, so I would write that next. Now I'm looking for x to the 4th. There's what, an x to the 4th here, and there's no other x to the 4th. So that would be 6x to the 4th. Now I want to see if I can find an x to the 3rd term. There's one here with an 8 in front. There's one here with a 4 in front. Can't I combine the 8x cubed and the 4x cubed to get 12x cubed? You see? Now, how many x squared terms are there? There's a 9x squared and a 7x squared. 9 plus 7 is 16, so that's 16x squared. And now the only other term that's left is 8x. And by the way, you notice how I use these check marks? That's to make sure I've accounted for every term. So this would be the traditional way, the conventional way of expressing this polynomial. And the degree of this polynomial is called 5. In other words, the degree of the whole polynomial is the greatest degree of each of the monomials that make up the polynomial. So, for example, if I had something like this, this is what, 8x cubed minus 7x squared minus 4x plus 3. The first thing I want you to notice is that by the add the opposite rule, I can view this as a sum of monomials. In other words, I read this as what? 8x to the third plus negative 7x squared plus negative 4x plus 3. And what would the degree of this polynomial be? The greatest exponent that appears is 3, so the degree of this polynomial would be 3. And again, notice the standard way of writing this, even though most people recognize that since add the opposite is the same as subtracting, they will still write it this way. In other words, either way is correct. But technically speaking, we write a polynomial as what? The sum of monomials. And I'd like to also show you, as we come towards the close of today's lesson, one more interesting thing that happens. Suppose I wanted to evaluate 8x to the fourth plus 5x to the third plus 6x squared minus 8x plus 5, okay? I wanted to evaluate that. And suppose I wanted to evaluate this when x was, say, 2.147. See, I put in 2.147, raise that to the fourth power, multiply by 8. Now I have to store that. Now I take the given value of x, raise it to the third power, multiply that by 5, add that. And can you see how tedious this becomes? One of the things I'd like to try to teach you is a new way to visualize this polynomial in terms of how it came about by using the multiply by x step. See, in other words, whenever you want to list this into a computer program, start with inputting x. Now, if the x is being multiplied by a number, the next step is multiply by whatever that number is. See, usually if there's a 1 over here, you can skip the step that says multiply by 1, because multiplying by 1 won't change anything. See, I start with x. What am I going to do now? Multiply by 8. That gives me 8x. What's the next thing I'm going to do? I'm going to add on the 5. That gives me 8x plus 5 so far. Now what do I do next? I multiply by x. That's going to give me what? 8x squared plus 5x, because each of these terms gets multiplied by x. Now the next step says what? There's a plus 6 over here, so I add 6. That gives me 8x squared plus 5x plus 6. Okay? Now what happens? I multiply by the input again. Now what's the next operation I see over here? It looks like it says subtract 8, so that's what I'm going to do. I subtract 8. Then to account for the x over here, I multiply by the input again. That's going to give me 8x to the fourth plus 5x to the third plus 6x squared minus 8x. And the final step says add 5. Now what's nice about this is this allows me to get this into the computer without having to memorize anything. In other words, what am I going to do here? Whatever the input is, I punch that in. I multiply by 8, right? Add 5. See, I'm not changing any settings or storing anything. Multiply by whatever the input is. Add 6. Multiply by the input. Subtract 8. Multiply by the input. Add 5. Do you see how simply I can press the keys on the calculator to do this? The only place I have to be careful is when there are missing terms. See, suppose I wanted to represent 8x to the fourth plus 6x squared plus 5 in terms of an input situation. See, what's missing here is what? The x to the third term and the x term. And whenever a term is missing, you can always put it in with a 0 coefficient. See, I can write this as what? 8x to the fourth plus 0x cubed plus 6x squared plus 0x plus 5. Now, if I want to handle this in terms of the calculator, what's the first step? Input 8, right? I'm sorry, input x, multiply by 8. Add 0, but adding 0 wastes a step, doesn't it? Adding 0 doesn't change anything, so you skip writing that step and then say what? Multiply by x. What's the next thing we do? Add 6. Then we do what? Multiply by x again. What's the next step? Add 0. Well, that's wasted, so don't bother writing that. Just multiply by x again, and then you add 5. So in other words, a quick way of defining this in terms of the calculator, 8x to the fourth plus 6x squared plus 5, is simply say what? Input x, multiply by 8, then multiply by x, then add 6, then multiply by x, then multiply by x again. And by the way, you could have abbreviated these into saying multiply by x squared, but it's just as easy to punch in the x, get the answer, then multiply by x again, and then you add 5. Now, today's lecture, I would say, is a housekeeping lecture. What I wanted to show you is that what's happened up until now is when we wanted to work with algebraic expressions, the only terms we had were either a constant times x or else a plain constant term. So if we got all the x terms onto one side of the equation, all the constant terms onto the other side, basically there was only one x term because everything was what? Modifying x. Now we have x's, x squareds, x thirds. Every time you multiply by the input, the exponent is going to increase by 1, and that is going to make the algebra a lot more complicated. But it's also going to become a lot more rewarding. It's like in any game, it's easier to play the game when there aren't too many rules. But when there aren't too many rules, there also aren't too many strategies, and the game becomes boring. It's harder to learn a game with lots of rules, but once you learn it, that game has much more scope and leeway for strategy. And polynomials are to advanced mathematics what place value arithmetic, or what place value is to ordinary arithmetic. The mathematician on the advanced level uses polynomials in much the same way that people who are doing ordinary arithmetic use place value. And we're going to be looking at that in our next few lessons. But rather than rush ahead right now, this seems like a good place to stop, okay? And to review, make sure you understand what a polynomial is, okay? Make sure you know what a monomial is. Make sure you know where they come from. Make sure you understand the vocabulary so that when we say coefficient or degree, you know what we're talking about. And again, that's one of the beauties of the tape. If as I say this to you, you say, what's he talking about? That's simply what? A reminder to go look at the tape again, okay? But anyway, until next time, study hard, have fun, stay young. See you soon.